Thanks for that, Heath. All right, so since the recording started and I'm seeing quite a lot of people coming in, we might get started. So welcome everyone. Thank you so much for coming. This is now session 2 of the Oh What a Lovely Molecule workshop. I've got my fellow SOC members in here. I still don't see Michael yet, but there's Heath there. So we're your friendly neighborhood organizers. Before we get into the talks today, I have some sort of housekeeping slides that I wanted to share with you. Just if I can find them. There we go. Just some general information about the workshop. Can you guys see I've got some slides? I'm not actually doing the
Yes.
slideshow, but that's all right.
Yes.
First things first, something that is a common practice in Australia before we start meetings and gatherings is to acknowledge the traditional owners of the lands on which we're meeting. This being an online platform, I'd like to acknowledge the Wallumattagal people, who are the traditional owners of the land in which I'm at the moment. But we'd like to extend our acknowledgement and our recognition of all the Indigenous owners of all the lands on which we're all meeting from. All the information that's necessary for the workshop should all be on the front page of the website. But just a reminder of some of the things, well, obviously the Zoom link, if you're here, then you've had the Zoom link. But we also have a conversation going on Slack. So if you could log on to Slack, we've got the link on the website. There's quite a lot of channels that are available for today's sessions and for the sessions for the rest of the week. Each individual session has its own channel. So if you'd like to join the conversation on Slack for each channel, please add yourself. I'm not sure if anyone's been frantically adding people onto those on your behalf, but please have a look and we can keep the conversations going, especially for the people who are joining us from different time zones who might not be able to make the individual talks. So the theme of today's sessions are all about the diffuse ISM and observing ISM and the challenges that come with that. This session, the talks are focused on RFI and the issues surrounding RFI, our good friends RFI. Very, very horrible. Before we get into that though, let me stop sharing this and start sharing something else, which is the introductory slides. I asked people to share an introductory slide, so I'm just going to try and pick on people. We'll start off with our presenters and scrolling. Bear with me. Did I get one from... I know I have one from Tommy. I might start with that one. Let me share my screen. So can you see that? So Tommy, would you be happy to introduce yourself?
Too late to say no.
Very much.
So one of these things is not like the other. I'm a little out of place here, I feel, because I'm more of a pulsar and FRB astronomer, so to speak, in that I'm a PhD candidate and my last project was searching for FRBs, but at the moment I'm working on RFI mitigation. I'm studying out of Macquarie University, but in conjunction with CSIRO. I use predominantly the Parkes telescope and the UWL receiver, which is the ultra wideband receiver low. I'll talk a little bit more about that in my presentation during this session. And you can see there's a picture of Parkes, there's a picture of me, and there's a picture of some of the data with some of the RFI that I'm working on identified. Yeah, so hopefully we'll all learn a bit about mazes and a lot about RFI, and anyone feeling a bit of imposter syndrome, I'll raise you your imposter syndrome with pure ignorance on hydroxyl masers.
Thanks for that, Tommy. And let me see. Oh, did I go past it? Or did I not get one? I don't think I got an introductory slide from Nobuyuki, so that's cool. No worries there. Okay, I'll stop sharing. One more thing I wanted to mention before. Oh, sorry. I do want to invite other people. Sorry, I got ahead of myself. Other people to introduce themselves. I'll also mention after we do some introductions, there's some shared documents that we're trying to compile. So, but sorry, I'm getting ahead of myself. Let me see if there's anyone else. Too many things going on at the same time. Bear with me. Okay, back here again. All right, Bank, I spotted you. Would you mind giving us a quick introduction?
Yep. Hopefully you can hear me all right.
You're a little quiet.
Oh, okay. Is that any better?
Oh, all right. Yep.
All right.
Yep.
Yep.
Yeah, we can hear you now. That's great.
All
Thanks.
right. Sorry about that. Hi, everyone. I'm Banawit Pimpanawat, but most people call me Bank. I'm now a postdoc at NARIT. Actually, I just finished my PhD last year from the University of Manchester. So my research so far has been about SIO masers in AGB stars. And I've done a little bit of 3D modeling of astrophysical masers as well with Malcolm Gray, who will be giving a talk later in this workshop. So the plot that I have there is just like one of the interesting results I got during my PhD, which is, like the V, like V is greater than zero SIO masers in Pi1 GRU. And so these masers just show that we actually have like an extra close companion in this source. And so it's now kind of like a hot topic in the, AGB people. So yeah, that's me. And I've also been involved in the commissioning of the Thai National Radio Telescope as well, which will be kind of like a highlight towards the end of this workshop about like the future projects and whatnot. So yeah, that's me. Thank you.
Well, thank you. And let's see who else we have in here. I saw Beth. Beth, I'll put you on the spot. Scroll up to yours. Oh, there we go.
Thank you. So I'm Beth. I'm a first year PhD student at Macquarie University. I'm also doing an Indigenous graduate research fellowship at CSIRO. So for my PhD, I'm looking at H2 region molecular cloud interaction and looking at molecular clouds through hydroxyl. So I'll be giving a talk on Wednesday about that. And the idea is we can use hydroxyl to trace this feedback. And I am particularly interested in radio interferometry. So I've got a survey on the VLA called the TORCH survey, which is an acronym for tracing something, something. It makes sense. Anyway, so we're looking at 13 H2 regions with that. I'm also on the gas cap OH survey data verification team, and I'm on one of the science commissioning teams for the Big Cat correlator for the Australian Telescope Compact Array. So lots of telescopes. I also have a Gaussian decomposition algorithm that I wrote, and I have some other interests there. But yeah, I'm definitely a hydroxyl person, I guess, but also ionized gas as well. So yeah, that's me. Thanks.
Thanks for that, Beth. You're definitely in good company. Esteban, if I could put you on the spot. So there you are. Would you be able to introduce yourself?
Hi, hello everyone. Great seeing you here, and thank you for organizing such a nice event. This is great. So hi, I'm Esteban Araya. Well, I used to work at Western Illinois University. Last semester was my last one there, and I'm adjunct faculty at New Mexico Tech. And I have been working for many years on interstellar medium type of that and circumstellar medium. Mostly studying regions of star formation, but also late type of stars in our galaxy, and some work done on other galaxies as well. And the little image here, I'm showing you some of the results on a paper in preparation with Wei Xian Tang, who was my former student and has been my collaborator for many years now, on detection of really broad OH absorption. And I'll be talking about that in a couple of nights for me. So here in the US.
Thank you very much for that. Let me see who else I've got. I think Jay, you gave me did you give me oh no, this is that Thaisa? Is that how you pronounce your name?
Hi, yes, I'm Thaisa Danilovic. I'm currently a research fellow at Monash University, and my interest is also in evolved stars. I like OH. I also like all of the molecules. I'm not that biased. And yeah, I mean, OH in particular is interesting for chemistry reasons and also things like mesophase-like distances, which are very important for our stars, which are otherwise quite hard to get distances for.
Thank you so much for that. All right, let me see if I can scroll through and find somebody else. John's already introduced himself. That's me. A lot of these people introduced themselves before. Jay, you're up.
Cool. Thanks, Anita. Hopefully all of you can see me. Hey, everyone. I'm Jay. I met some of you in person. I worked with some of you, and I'm looking forward to meet rest of those who I haven't met or worked with. So I've done my PhD at University of Tasmania. My primary work during my PhD was in VLBI spectral line astrometry, where I studied high mass star forming regions, measuring their distances and the galactic structure, especially focusing towards the inner Milky Way. I've also I've studied measures in all all these main lines, both methanol measures, water measures, and now in my postdoc I'm doing studying hydroxyl measures. I loved methanol and water measures, bit of a controversial thing to say over here, mostly because there's no ionosphere issues over there when you're doing astrometry. There's a picture of me, more points if you can guess which radio telescope is behind me. Definitely Tomoya is not allowed to guess that. This is down below is one of my work during my PhD, where I studied the extraordinary outburst that happened back in 2015 in high mass star forming regions NGC 6334, and the flares keep going, and then there's spot maps. Yes, that's not Iriki. That's now I forgot the name. Mizusawa. That's Mizusawa. Or maybe that's it. It's called Iriki. Okay. Tomoyo can help us with that. So yeah, that's me. My current position over here is at GasCap postdoc, and there's people who are interested in GasCap data. There's some good news on that. More on that when Joe gives a talk on Friday. I'm working with Joe Dawson in this project over here. So yeah, looking forward to more talks and catching up with all of you during the rest of the workshop.
Awesome. Thanks, Jay. So let me see who else we have. Oh, Allison?
Yep. Hi there. My name is Allison Smith. I'm currently an assistant professor at the University of Puerto Rico, Mayagüez. My background is in mostly studying the atomic to molecular transition with molecular spectral lines, including OH, and in particular in intermediate velocity molecular clouds. Before my position here at UPRM, I was a postdoc at Arecibo. That's where most of my OH work was done. And I spent, or actually in the first session of the workshop, I gave a talk on observing or not observing, as the case may be, OH in diffuse gas, and in particular in the intermediate velocity clouds. So looking forward to discussing with you all throughout the week and joining this workshop for the very first time. And thank you very much to the organizers.
Thank you, Allison. Okay, let me see if Rachel.
Hi, my name is Rachel. I'm a PhD student at the University of New Mexico. I just finished my second year. I work with astronomical masers, particularly SIO, and I just started working with OH masers, so I'm looking forward to learning a lot more in this workshop. I mostly work with VLA data, but I'm also interested in machine learning and modeling, specifically looking at mass loss rates, SED modeling, and determining distances. And I'm working with Ilva Filstrom and Laurent Sauerman as a part of the BADA group.
Excellent. Okay, thank you so much for that, Rachel. I'll stop sharing now. I wanted to, though, just before we get on to the talks, because I mentioned this before, I got ahead of myself. On the website, I've also put a link to the code of conduct for the workshop. It's just a code of conduct from the University of Sydney. It's pretty standard stuff. You know, we expect everybody to be collegial and polite, but I also want to invite, if anyone, if there's any concerns that you have or any problems, please feel free to reach out to either myself or to other members of the SOC, and we'll sort things out as swiftly as we can. We also have some documents on the share drive that I'll keep bringing up here and there. Which is if people have expertise or experience with certain telescopes and would like to be involved in other projects with other people, or would like to, you know, offer themselves as a helper if people want to use telescopes. We have one of those going at the moment. There's some discussion on Slack about that. But yeah, we'll jump right into the first talk, which will be Nobuyuki Sakai.
Okay, so good afternoon, everyone, and thank you very much, organizers, for this exciting workshop. So today, let me briefly introduce the challenges of developing an automatic RFI flagging script for the 40-meter TNRT. This photo shows our telescope, 40-meter Thai National Radio Telescope, and the L-band receiver developed by Max Planck Institute for Radio Astronomy is put at the prime focus of this telescope. Today, I will introduce how to challenge mitigating the effect of RFI on our TNRT data, and I'd like to discuss with all of you how to improve our data reduction scheme by discussing with all of you. So thank you very much for this good opportunities for us. So in the first half of my talk, let me briefly introduce my institute and our radio project. In the latter half of my talk, I will focus on the main topic, RFI challenges. I'm from NARIT and NAOJ. NARIT is National Astronomical Research Institute of Thailand, and this is supported by our executives, Director Sam, the Deputy Director Wipu, and the NARIT founder, Professor Bun Laksa. And also we have science advisors, for example, Busaba Kramer from Max Planck and Malcolm Gray. They will also join this workshop. And in NARIT, we have the Center for Radio Astronomy and Engineering, consisting of two groups, Thai National Radio Astronomy Observatory and Advanced Radio Frequency Laboratory. This group is led by Dr. Koichiro Sugiyama as the CRA manager. Now I'm working in the TNRO, Thai National Radio Astronomy Observatory, as a commissioning scientist. As introduced by Bank, we have an excellent postdoc, Bank. So now me and Bank are mainly involved in the commissioning of the 40-meter TNRT. And also we have a VLBI project, but today let me focus on the single dish project for the 40-meter TNRT. So this is our telescope, TNRT. So far we have installed 2 receivers of L-band and K-band. Of course, L-band can be used for observing OH molecule, the main target of this workshop. Our telescope can cover the frequencies between 0.3 and 115 gigahertz. The total surface accuracy is expected to be about 150 micrometer in the manufacturer specifications. The best pointing accuracy is expected to be about 2 arcseconds, allowing us to observe at high frequencies up to 115 gigahertz. This telescope is very fast. For example, an azimuth driving speed of about 3 degrees per second can be achieved. And today I will focus on the L-band receiver due to the concept of this workshop. We made an announcement for call for proposals, Thai National Radio Telescope Cycle 1 in the last December. And now we are running Cycle 1 science observations between March and August this year. And this shows the rough timeline of development and commissioning for the 40-meter TNRT. We have a lot of commissioning items such as K-band. This commissioning is led by our postdoc, Bank, who is attending in this workshop. And also there are many demands for polarization studies using the full Stokes backend. This is also our important commissioning item. And also VLBI, CXKU bands, and QW bands. So from here, let me move on to the main topic of this session, the challenges of developing an automatic RFI flagging script for the 40-meter TNRT. So we have created our own data analysis script for the telescope. Our telescope can provide the output file with the format of MVFITS. MVFITS is the multi-beam fit file. This MVFITS consists of a lot of subscans, and this file format was originally developed for multi-beam observations, if my understanding is correct. And left-hand side shows the basic procedures for single-dish spectroscopic data analysis. For example, Sakai and baseline subtractions, TC star determination, the unit conversion from Kelvin to Jansky, the Doppler correction, and the average of multiple files. And this data reduction can be done using the AstroPy packages. And now we have to flag RFI data manually by eyes. So I'd like to improve this procedure. That's why I'm attending this workshop to discuss with many of you. For example, the upper panel shows a good TNRT data. However, the bottom shows a bad file affected by RFI. We have experimentally found that many RFIs are polarized. For example, this orange shows horizontal polarization, while blue is showing vertical polarization. TNRT L-band data is recorded as linear polarization. And now I'm developing script to flag RFI effectively. So I'm referring to one paper, H1 FAST, H1 data calibration and imaging pipeline for FAST, written by Jin et al. 2024. For example, top panel shows RFI categories from GPS and satellites. And they showed a method that the mean value of radio power is shown as a function of time. And the top line shows the average of all spectral channels. We can see 3 bursts due to RFIs here. here. And also they are showing the difference between subsequent channels. We can see similar burst due to the RFI here, and here. So based on the reference for the first telescope, I'm now developing script for the 40 meter TNRT. Sorry. For example, top left shows the raw data of V polarization obtained with the 40 meter TNRT, and this shows the radio power as a function of frequency, and we can see the effect of RFI around 1666 megahertz, and the top upper right shows the same data, but showing the frequency and time domain. We can see clear impacts by RFI. And also, by referring to the first paper, I'm now showing the median value of the radio power as a function of time. And if the horizontal black lines show plus minus one sigma of this mean value. So if I flag values larger than and smaller than the 1 sigma clip, then I can create improved data as shown by the lower left panel. This shows the data with RFI flag, and vertical axis shows the radio power, and horizontal axis is the frequency. And upper right shows the same data with RFI flag. White masked regions are not used when averaging radio recorded data. So in the near future, I'd like to make automatic RFI flag for the 40 meter TNRT data. But still, I have several considerations. For example, how to define a good threshold, and also that threshold should flag only RFIs and should keep the good data. So I have to think how to make a good threshold. And also, perhaps I have to consider another approach. After my talk, we will see and listen more RFI mitigation techniques. So I'd like to learn from the second talk. And yeah, my collaborator suggested me to think about, for example, the machine learning and the classification for the RFI mitigation. And now TNRT Cycle 1 science observations are conducted, which will be continued until the end of August this year. And we plan to provide analyzed and evaluated TNRT data to individual PIs. But if requested by PIs, we plan to provide the TNRT raw data and the Python analysis script to individual PIs. So in the next few months, I have to complete to make this automatic RFI flagging for TNRT users. And before ending my talk, let me advertise that we welcome your scientific ideas and proposals for the TNRT Cycle 2, which would be announced around this September or this October. This is not yet fixed. So let me summarize my talk. Today, I introduced the Thai National Radio Astronomy Observatory, TNRO. This operates the 40 meter TNRT, and relevant spectroscopy model is now ready for science. But there are many commissioning items such as the K-band, Flustox backend, VLBI, CXK bands, and QW bands. And also, I also introduced my recent activities, how to flag RFIs on the TNRT data. Yeah, I'm now taking inspiration from the first team's methodology. Frequency versus time versus power is a good domain to effectively flag RFI. But if you have any good ideas, I would appreciate it if you could let me know. And also, if you have any collaboration ideas with the 40 meter TNRT, please feel free to contact the manager of CRAE, Dr. Koichiro Sugiyama, or me. I'm a NAOJ NARIT MOA compliant behavior scientist. focusing on the commissioning of the 40-meter TNRT. And also, we have many collaborators, for example, Bank, Pusaba, Marco. They all are joining and will join this workshop. So please contact with any of us. That's all. Thank you for your attention.
Thank you very much for that. It seems like a really, really big task to to get a new telescope underway. So good work on that. Do we have any questions? Wahid?
Well, hi. Oh, someone raised their hand. I can wait.
Please go ahead.
Oh,
Esther.
okay. All right. Well, nothing. It's a really nice talk. I didn't know about the telescope, so thank you for letting us know about the status of that instrument. I don't have a question. I just have a little comment for you to consider now that you guys are kind of creating the documentation for the telescope. Is the calling the vertical polarization V pole maybe a little bit confusing for some people who may be expecting V to refer to the V-Stokes. So something for you guys to consider when you're writing your documentation is perhaps use a different nomenclature like X and Y, for instance, for the linear polarization that is more standard. Really nice talk. Thank you.
Thank you very much for the important comment. Yeah.
Yes, thank Nobuyuki for the talk. I would like to have some questions about the sources of the RFI over here. I think that in some slides you show the sources of the RFI would be from the GPS, would be some from the satellites. Are there any kind of other sources for the RFI in your area?
Yeah, thank you very much for your comment. And let me show you these slides. Yeah, we have also investigated RFI environment at our site, and we have found that the most impact is coming from a mobile base station. So yeah, this is our case. And yeah, and also sometimes radar is affecting our data. And now we have a frequency management group. In this group, people are collaborating with, I cannot remember exactly, but yeah, our NARIT staffs are collaborating with Thailand people who are involved in frequency protection and management. So yeah, of course, H1 is protected for astronomy purpose, and also yeah, we are trying to protect other important frequencies. But of course, we have to how to say, collaborate with general people. So general life is also very important. So we are collaborating and discussing with local people as well to make our site RFI silent as much as possible. But to your question, yeah, in our case, the biggest impact is coming from mobile base station. Yes. I hope this is answer to you.
Yeah, thanks for that, Nobuyuki.
Jay?
Yeah, thanks, Anita. Hello, Nobuyuki-san. Good to see you again. You remember we met at the 2023 major symposium at Kagoshima. Regarding your last slide where you're summarizing your talk, nice talk, by the way. Thanks for giving us all the updates. What are the timelines that you see for the, or I'm sorry if you have already mentioned this, what are the timelines you see for the C-band when it finally gets fully operational? And I'm assuming that the K-band is the next, priority to fully get it fully science ready. and after that, I'm assuming it's C-band. So what are the operational timelines that you see that you'll have? Yeah.
Yeah, thank you very much. Yeah, K-band is now high priority, and yeah, we would like to open this K-band mode to the community in this year. Yeah, bank is working so hard. And regarding the C-band, yeah, our receiver can cover frequencies between 4.55 and 13.65 gigahertz. And the receiver itself was already developed by a Chinese institute, and we are having this receiver into our laboratory at the NARIT headquarters, Thailand. But we have to develop feed horn, and also we have to design our optics. So yeah, in original plan, we would like to install this receiver this year. And after the installation, of course, we have to evaluate the science capability of this receiver. So we would like to complete everything in the next year, 2026. But yeah, it's subject to change. But this is our rough plan. K-band was already installed, and now bank is evaluating this receiver. And CXKU bands will be installed this year, hopefully. This is the current situation, and thank you very much for your question.
So yeah, thank you so much. Just to add on that, so I can see that you have put down VLBI in front of the the C band. So so before installing or before having the C band fully operationalized, you will be testing, or you'll be operationalizing VLBI with K band and L band. Am I correct in assuming that?
Yeah, thank you very much for the comment. Today, I didn't explain the VLBI in detail, but regarding the L-band receiver, we have succeeded in getting VLBI fringes among our telescope, FSB 100 meter, the first, and TMR 65 meter. And also, we are now planning to collaborate with other telescopes such as CSIRO telescopes and also GMRT and so on. So yeah, for L-band, yeah, we have succeeded in getting VLBI fringes, and yeah, but for K-band, yeah, we will try to do VLBI fringe check observations. Yes.
Thank you.
Yeah.
Are there any more questions? Before we move on to the next speaker, I wanted to also take an opportunity to mention, and thank you so much for your talk. It was so interesting to see the new telescope. There's also going to be another session on Friday where we talk about new ideas for this telescope, for the new telescope in Thailand. So that'll be another opportunity for people to discuss how we might be able to use your new telescope. So thank you so much for that. And now thank you. And now for more perspective on RFI, we've got Tommy.
Okay, bear with me while I grandpa my way through share screen.
I feel you.
Oh, all right. Okay. So once upon a time, I was invited to speak at this conference about RFI. So we're going to take a long winding route through my current research, which is applicable to pulsars, and by way of analogy, apply that to OH masers. So similar to a YouTube video, you'll get what you're actually wanting at the end of this presentation, but you can't fast forward through it. Don't forget to like and subscribe. Okay, so another quick introduction. I'm Tommy Marshman. I'm a PhD candidate. I'm supervised by Joe Dawson. You probably know her from the literature as J.R. Dawson at Macquarie University, and co-supervised at CSIRO, which is the Commonwealth Scientific and Industrial Research Organisation of Australia, by Dr. George Hobbs. I'm about halfway through my PhD. I'm part-time, probably a little bit too part-time, and Joe hates it when I refer to myself as a hobbyist. I'm currently working on removing Bluetooth and Wi-Fi from the Parkes ultra-wideband receiver data, which is not the same band of the UWL as Mazers, but I'll get onto that. Okay, so Parkes, for international people, Parkes, or the Muriang Telescope, is located in Parkes, New South Wales, Australia, and it's a fairly regional town. It's outside of Sydney by about 500 kilometres inland. There's a picture of the telescope there, and on the right is the ultra-wideband receiver low, which covers 703 megahertz to just over 4 gig. And it's called low because it's part of a larger project to put in an ultra-wideband receiver mid and high, with the aim of being able to cover from 700 megahertz all the way up to 24 gigahertz. And so they've only put the low on the telescope at the moment. To give you an idea of the direction my presentation is going to take, first we'll give you a brief introduction to pulsars, because it'll explain some of the rationale behind the methods I've been using. We'll define RFI, the Bluetooth and Wi-Fi, describe the Bluetooth and Wi-Fi more specifically, talk about how we've mitigated all the processes we've chosen to test and how far we've gotten with our tests, the next steps, and then how some of those methods could be applied to OH mazes and observations in your band, or the band of interest for you guys. All right. So I don't know, there's no GIF showing on my presentation, but there it is. Okay, so pulsars are stellar remnants of massive stars between 8 solar masses and 20 solar masses, and after they supernova and collapse, what's left of them is held up by neutron degeneracy pressure, any higher than about 20 solar masses, and they continue to collapse into a black hole. So what's left is a neutron star, and because the angular momentum of the star is preserved, they're relatively fast rotating. In the image there, it's slowed down. And because they're quite dense and compacted, they have very strong magnetic fields. So from the magnetic poles of the pulsar, there's strong radiation emitted. And when the magnetic pole is not aligned with the rotational axis, we get a lighthouse effect there. And you can see in the bottom panel, the power picked up by the telescope peaks as we get beamed by the pulsar. And so on the x-axis of that, that's time, and the y-axis is power. So working more in the time domain here. And as you can see, there's only one pulse in that bottom panel. So that's sort of a pulse period of the pulsar, which comes into later on when we work in pulse periods and folding, which I would explain a bit more. Okay, defining RFI. So for my purposes, radio frequency interference is just anything that is non-astrophysical. So, and it's everything is by that definition terrestrial then. So in the Parkes UWL 2.4 gigahertz subband, which I was using, it includes the NBN, which is Australia's national broadband network, which is the wired and wireless internet infrastructure, open access internet structure. Bluetooth, which everyone's familiar with, which is short range connection between devices, and Wi-Fi, which is wireless internet. But my work is predominantly focused on mitigating the Bluetooth and Wi-Fi. So we can describe and characterize the Bluetooth and Wi-Fi pretty well because it is terrestrial and man-made, or anthropomorphic. So it operates with very tight specifications, so it makes it easy to characterize. So Bluetooth and Wi-Fi are in the range of 2400 to 2480 megahertz. And this puts it in the 13 of 26 subbands for the UWL, which is centered on 2432 megahertz. And in setting our mitigation techniques, we use the brightest known pulsar VELA, which is there in its, so we designate pulsars by RA and DEC, unlike you guys that use galactic coordinates. And we can describe Wi-Fi because it is man-made in 3 dimensions, so power, time, frequency. We also note that it's intermittent in both time and frequency. So here's the problem for when observing pulsars. In the top 3 panels going horizontally, we have a clean band, which is centered on 1408 megahertz. And so 3 products that we're interested in are a pulse profile, which is folded. And if you imagine that pulse profile that was underneath the image before, we just take period snapshots of the period of the data and overlay it on top of each other. And as we overlay it, and which is called folding, it brings the signal, raises the signal higher than the noise. So you get a nice pulse profile there, and it's dispersed there because of the electron density of the intergalactic medium and other things that it's traveled through to reach Earth. We get a pulse profile there. That one's split because of aliasing, but also you notice in the far right-hand top panel that there's quite a well-formed bandpass that you can see there. You know, compare that with the bottom panel, which is the band that I'm interested in. You can see in the pulse image on the bottom left, it's overwrought with RFI. So you can't really see a pulse profile at all in that image. Then a pulse, sorry. And then in the center bottom, the pulse profile is not distinct and not clear because of the baseline from the RFI. And in the band pass, you can see because of the power of the RFI, it flattens out the band pass. So you can't really get much information out of that there. And you can see how powerful those 3 spikes are, which are the Bluetooth advertising channels. So those are devices trying to ping each other because Bluetooth's quite needy. So even when it's not connected, it's looking for someone to talk to. Okay, so classifying the Wi-Fi and Bluetooth RFI in 3 dimensions. In the left-hand panel, you can see a dynamic spectra with time on the x-axis and frequency on the y-axis. So you can see that both in time and frequency, it is quite distinct. You've got vertical rectangles and horizontal rectangles and little dots all over the place. So and because of the power, it's quite well defined in time and frequency. Then on the right-hand side, you can see the baseline astronomical signal is quite low compared to the power of this, which is an advertising channel from Bluetooth. So it massively overpowers the astronomical signal, but also allows us to differentiate quite well because of power. Okay, and in this one, I've highlighted some of the RFI so you can identify what it is. The Wi-Fi is vertical, the Bluetooth is generally horizontal, all those little specks, and the NBN, which we didn't deal with much, is down the bottom. Here it is in 3 dimensions. And if you watch it, you can see that the massive peaks, noting that this is a logarithmic scale, so that the RFI, to give you an idea of how powerful the RFI is, you can see those peaks with the yellow peaks. So the Bluetooth, the NBN is closest to the screen along the bottom. And you can see every so often there's a pulse profile that comes up. And so here's a snapshot of the image with some of all of those elements in there, except for the Wi-Fi. So you can see these are Bluetooth. This is the National Broadband Network. And there's the pulse profile running from the top to bottom in the data. And there it is again without the scribble on it. Okay, so mitigating. Currently in the band that I'm interested in with the Bluetooth, rather than mitigating it, they just excise the whole 80 megahertz, which is 80 megahertz out of the 128 megahertz band. And we found that because it's intermittent in time, if we can do something more targeted to the RFI, we only have to remove 3.6% of it, which means we can recover about 96% of the data for scientific purposes again. So in those images on the bottom left, that's the full bandwidth of the UWL from 703 megahertz all the way up to the 4 gigahertz. The big white block sort of in the middle, adjacent to the arrow, is the middle subband, which is 13 out of 26 that I'm interested in. And you can see it's the biggest part that's just been removed. And in the middle, that's how big the panel is, how much of the band is just excised and not used, which is 66% of the band, which is just thrown out. And then on the right-hand side, you can see how little of it is actually RFI that we could recover. Okay, so we've decided to test a number of techniques: a simple voltage threshold, spectral kurtosis, match filter, and demodulating the actual signal and removing it from the data that way. So as mentioned before, because the RFI is so powerful, applying a voltage threshold that keeps in all the astronomical signals should be the simplest one to implement. And as mentioned, we're using the most powerful pulsar that we're aware of. So if we can keep the most powerful signal in the astronomical data, cutting anything else off should keep enough data to make new discoveries. And that's just an arbitrary line put in there, for example, the red, but that's to give you any idea of how much of the data the RFI we can get rid of. So here is another dynamic spectra. On the left, it's with no mitigation, and you can see that because of the power in the RFI, those yellow peaks, it mutes the astronomical data, and you can see that the pulse profiles aren't as distinct. Whereas if we implement a threshold, which is closer to the astronomical data, you can see how much more distinct the pulse profiles are. You can even see there that we've recovered the shape of the bandpass there with those two yellow sort of horizontal bars across there as well. And here's, again, in 3 dimensions. And on the right, you can see that the pulse profile is just a lot more distinct and a lot more usable for scientific purposes. And so the folded pulse profile, this is folded again. So it's along the x-axis in the dynamic spectra, it is only one, the time length is the period of the pulsar, and the frequency isn't labeled correctly there. You can see the pulse profile, and you can see a much cleaner and well-shaped bandpass there as well on the right-hand side. Now, another method which is only usable in fold mode at the moment that's already on the telescope is spectral kurtosis. And basically, kurtosis measures the shape of the Gaussianity of the noise. So if you look on the right there, you've got the teal or cyan one in the middle, which is relatively Gaussian, and then you've got some of the other kurtotic ones where there's less peakiness and more tails. And so on the right, we've got samples from our data, and you can see that the grey filled in histogram there is a lot more Gaussian than the other ones because it is the astronomical noise. So it's a lot more random. and the dark one there is the pulsar, and again, it's got that shape, whereas the RFI has a much bigger tail and is a lot more leptokurtotic, so that it's got a lot more noise that we can cut out and those thresholds. So by applying different methods of spectral kurtosis, so the way the kurtosis works is it takes a sample of the data at the start of the observation and then uses that to create an estimator, assuming that that's Gaussian, and then anything that deviates from that can be excised, assuming that it's non-Gaussian because of the content of RFI within it. So again, you can see on the left-hand side, it's overwrought with RFI. The bandpass is flattened out because of the power of the RFI, and there's no pulse profile there. On the left, with just the default kurtosis settings, we can recover a lot more of we can recover a pulse profile and a lot more of the bandpass. So again, okay, a match filter, again, because it is quite distinct in frequency and time, we were applying a match filter to basically channelize the data and run a top hat convolution through it. And as you can see there on the left-hand side, there's no mitigation applied. On the right, in the center, we've applied the identification of it. So it's identified a fair bit of the RFI. And on the right-hand panel, we've substituted those identified areas with random noise to replace it. As you can see, there's still quite a bit left there, but we're working on it. Okay, and finally, mitigating the RFI by demodulating the data. So basically, because it's Bluetooth and Wi-Fi and it's well structured and there are protocols of how it's encoded, we're able to actually get the Bluetooth data and break it down into the bits of information. So in that picture there, you can see that the points to the top are the ones and the points to the bottom are the zeros in binary data. So that's actually a binary signal, and the 1010, the spiky stuff at the start, is how the Bluetooth, they set the timer for each other so they know what bit rate each device is using. So they're basically communicating to the receiver device the speed of the data transmission so that it can decode it in the right way. And we're experimenting at the moment at using, again, there's an arbitrary threshold there, but mitigating the signal based on how far it deviates from the central frequency of each frequency channel there. And we'll get back to you on those results. So the next steps, they all end up with rather similar results in terms of spectral kurtosis, in terms of mitigating the RFI and recovering the data. Spectral kurtosis needs more online testing. The match filter needs improvement, but the voltage threshold is simple and actionable now. We could basically do that to, you know, most of our data now in that our band. So one of the problems is defining how good is good enough. And it sort of goes back to Nobuyuki's point in his talk about where to put the threshold for the RFI mitigation. And I'll talk about that a bit more now. So applications to OH mazes. In the UWL, the OH spectral lines are in subband 7 of 26, which is 1600 megahertz to 1728, and it's centered on 1664, which is almost bang on one of your main lines. The RFI inside this subband are the Iridium GPS satellites, as Nobuyuki identified, and also in Australia, the Telstra is one of our mobile or our phone telecommunications companies. So the handset towers are from 1710 up to 1728 and into the next band. And so you can see that the Iridium satellites, while the main peaks, the main lines are for OH in a sort of clean area of the band, the satellite lines are in RFI territory, which is the handsets and Iridium satellites. But as you can see, I took a snapshot of the data down below. They are also well defined in time and frequency and intermittent. So they're quite similar to the Wi-Fi and Bluetooth. So the methods we're using to mitigate the Wi-Fi and Bluetooth should be applicable to the RFI in this OH maser band as well. So here's a close-up of that. You can see up the top of the image is the Iridium satellite signals, and it looks quite similar to Bluetooth, and down the bottom is the Telstra handset signals. And there's a comparison with the data that I'm using, and you can see it's somewhat similar in size and, well, not size and shape, but shape at least, in that it's well defined in time and frequency. Okay. Now, so I did a quick test with a voltage threshold, and so these are the band passes. On the left, it's before the threshold, and you can see all the spiky stuff on the left of the band pass is the Iridium satellites, and the stuff towards the right is the Telstra or the telecommunication handset towers. I've applied the threshold on the right, noting that the power is in a log scale. And you can see I was able to get rid of a lot of the Iridium satellite stuff. So that suggests that it might be at a higher power than the telecommunication stuff, because it did remove a lot of the telecommunication stuff. But it does highlight, and I'm just using this as an example, I know those aren't maser lines or OH lines there, but one of the problems with setting a threshold is you'll keep your data, but you'll also keep any RFI that is below the threshold. So it could still influence the data that you're trying to use. Now, the problem with that is if you lower the threshold too much, you'll get rid of information you'll need. And my understanding is you need the peaks of the lines to do your science. And so here is an example with the H1 line, where on the left, there's no mitigation used. And on the right, I deliberately lowered the threshold too much, so it truncates the spectral line. And so I believe if I truncated that spectral line, you're not going to be able to do the science you want to do with it, because you don't have the peak power of it anymore. So that is one of the things, as Nobuyuki mentioned, and I've mentioned already, is finding the right threshold to cut out what you don't want and keep what you do want. Okay, so the next steps for the OH maser stuff in that band are quite similar, is that it's defining how good is good enough with the threshold if you want to use a voltage threshold, and working out acceptable thresholds for spectral line science, whatever that is. As I said before, I'm quite a novice when it comes to this stuff. Okay, and that's it.
Thanks for that, Tommy.
All right.
As always, I always look forward to your slides. You always do the best presentations. Thank you so much. Do you have any questions?
Oh, yes. Thanks, Tommy. Really nice talk. I think I do have some data from Park English for observation of H1 in the in the nearby dwarf galaxies of the Milky Way. So they're in the spectra, the raw spectra, even before the calibration, I saw a lot of RFIs around that. So I just want to ask if I can use some of your technique to get rid of the RFI, because the signal from H1 signal from my data is very faint. It's just like about less than 1K. Yeah.
I think you should be able to use it because you average over about, is it a minute for each?
No, it's for each pointing. For
Yeah.
each pointing is about so about 10 minutes actually. I observed, yeah, I observed with a very you know, high, very high sensitivity. So quite long intercalation time for each pointing. So I
Yeah.
remember it's about more than 10 minutes per each pointing.
Okay.
So, but I consider a lot of RFI over there, and another problem is that to subtract the continuum. I saw the continuum, right? Yeah, how best to subtract the continuum. Again, because of the H1 signals from the nearby dwarf galaxies of the Milky Way, very faint. Yeah.
Okay.
Yeah.
I'm out of my depths to comment on the continuum subtraction stuff. That is a phrase I'll have to Google after this. But I think with the integration times, because it's averaged, applying a voltage threshold should work to help bring that signal to noise for the H1 lineup for what you're looking for.
So I mean the H1, I don't know the try to get very high sensitivity observations over there. And so the H1 in terms of Kelvin in the nearby dwarf galaxies or the Milky Way, it should be like just about what, like a few hundred milli Kelvin, for example.
Okay.
Yeah. I can see it towards one dwarf galaxy. I can confirm that there's H1 over there, and compare with the previous data from gas survey from so passing dish, I can confirm that there's some little H1 block right there. Yeah, but I think that we can talk about that on the chat.
Yeah. That would work because I think there's a lot of background stuff I've got to actually research to answer your question. Yeah.
But thank you so much for the talk.
Yeah, no dramas.
Seba?
Very nice talk. Thank you there. Let me lower the hand there. A question here. So in this idea of the danger, right, of using a very low threshold that you will end up removing your astrophysical signal, I was wondering if you consider checking whether the signal is polarized or not, because the RFI tends to be polarized, right? While in many cases the astrophysical signal is not, certainly the H1, right? So by looking at the polarization, you may be able to know whether it will be a good idea to apply the very low threshold or not in the signal. Have you given any thought to that?
Yeah, a little bit. So yeah, like you said, because it is it is often polarized. So we find that in there's pole A and pole B, one of those will have a distinctly higher level of RFI than the other one. And sometimes it's almost completely, say, from memory, I think it's polarization B where we notice the highest levels of power in the RFI, and sometimes it's almost absent, I'm pretty sure, in polarization A sometimes. Yeah. So that's a good point. Maraming salamat.
But are there any more questions for Tommy specifically? No, cool. So if we can, if I can kind of make a comment, which will maybe hopefully try to generalize the discussion a little bit more. I think it's really interesting that you pointed out that, of course, all of the RFI signals that are there are man-made, which therefore means that somebody has a definition of them somewhere. I found that it's very, very difficult to actually get any information about the nature of the signal, like say from the telecom, or from the actual sources of that. I just wonder if maybe if anyone here, or if maybe Nobuyuki or yourself, Tommy, have tried to seek out any of that information, like directly from the source of the RFI, of what is that, the nature of it?
I've found Bluetooth and Wi-Fi has been pretty, especially Bluetooth, it's really well documented. So I think part of it is so it might not be the case for the Iridium satellites, because there'll be some sort of proprietary knowledge or something there, and but what I think is the rationale behind it is they want people to know about their protocols and use them so that they actually make money off it. Yeah, so these device manufacturers and engineers need to know how to use Bluetooth and Wi-Fi, and similar with Iridium satellites, I suppose, to actually make their products and not make them, because if they're too secretive, they'll make themselves redundant if no one uses them.
Well, John?
Yeah, so the people who are installing the national broadband on the towers do have to report to John Reynolds at the CSIRO about what frequencies and what powers and what directions their transmitters are pointing. They have to report to the UTAS as well, because we have an observatory. Now, if they are close and above a certain level, John has the power to object and ask them to reduce that. But it's a very difficult thing to determine. But if you do want to track some of that down, you could check in with John Reynolds at CSIRO.
I wonder if more broadly, if people who are working with other telescopes in other areas might then look and see if there's any, like whatever regulatory body governs the radio frequencies that people are allowed to use. I imagine that they would have some way of at least identifying what it is that people are emitting and what the limits around that are, and that might be at least a partial approach to trying to mitigate it, if you at least know exactly what the signal ought to look like.
Well, there is a big international forum every 3 or 4 years, the so-called WARC, W-A-R-C conference. And for many years, Tasso Tsumis was representing Australia at that. They usually meet in Geneva. So if you sort of want that kind of info, I'm sure Tasso can give you a lot.
I suppose another point that that you touched on, Tommy, and by the way, thank you for coming and giving a talk. I know that it's out of your science expertise, but thank you so much, because it really is so valuable for us to have a look at the ways that RFI can be mitigated. I think you made a really good point about how a lot of the RFI is of short duration in time. I know that when I'm looking at my own data, because I have some maser monitoring data, and if I were to apply a flux threshold or signal threshold and flag anything above that, I would flag out my masers, and that would be problematic. However, if I have a rule, and I wrote some code that does this for my data, but it's great to hear what you're doing. Maybe I can make that a lot more robust, sounds like. But I found that sometimes if you're only looking for things that not only are above a threshold, but also are outliers in time, I find that that's a very effective way. So when I have, say, a 4-minute integration, I keep the integration stage until the very, very last step, and I do my RFI mitigation before then, when I still have 1 second time dumps from the telescope. And I think that approach has allowed me to save a lot of my data. I don't know if anyone else has any experience in doing something similar.
Yeah, that makes a lot of sense. So you mean you throw, because then you're only throwing out a second of data rather than throwing out the whole.
Exactly. Yeah, yeah. And I'm able to recover a lot of signal underneath that. And I even find some of the this is another thing that I found in 700 megahertz band, which this is for CH, so it's not OH. But there's some CH transitions down around 700 megahertz, and that band is just horrific for RFI. But there is definitely a pattern to it, and when you've spent as many hours staring at spectra as I have, it's very recognizable. A lot of it is, say, every fifth channel in frequency space is rubbish, and I'm like, okay, well, let me take out every fifth channel. I've tried doing like clustering algorithms of seeing, how many channels are above a certain threshold, and trying to do this is all sorts of. None of it ever worked, unfortunately. Maybe I should talk to you a bit more about that so I can recover my 700 megahertz stuff.
Well, that's interesting because I think 700 megahertz is also mobile phone towers as well.
Yeah, it is.
And that's it. Yeah, interesting as well. I wonder if there is a periodicity to it, because then that would make it easy.
Yeah. Typically the periodicity that I see is in the frequency domain, so it's like little pips, and it seems to be persistent in time, but I feel like I can see things underneath it because of course it's weak signal I'm looking for anyway. So, but with stuff that's that narrow in frequency, it's actually kind of good for us because as the Earth moves around the sun, our relative velocity relative to these sources, like the astrophysical sources, does shift regularly. So these fringes in frequency space, since they're terrestrial, they move around, and I can kind of see through them if I can trust that that's what the form of it is. So there might even be some space to do that kind of removing if it's every certain frequency channel.
Okay, yeah, it's kind of like, I don't know, trying to take a photo between the pickets of a picket fence as you drive past.
Exactly. It's exactly what it feels like.
It seems to me that the RFIs has some kind of, very characteristic features. Then, do you think so? Yeah. So I think that Nobuyuki talked about using, machine learning techniques to classify or identify the RFIs. Would you please to get more information about that, Nobuyuki? I think because to me, machine learning is kind of very good at, I mean, the neural network, for example, is really good at extracting the kind of the features of something repeatedly, like yeah. So Nobuyuki.
Yeah, thank you very much for your comment. Yeah, to be honest, I just started this project recently, but recently my friend attended the conference and he learned how to mitigate RFI using the machine learning. So to be honest, I have not fully understood the technique, but yeah, machine learning is good at the classification problems. So my rough idea, firstly, I'd like to classify good data or bad data using the machine learning. And if we can get only bad data, we can apply a RFI mitigation script, such as voltage threshold or something. So firstly, I'd like to classify good data and bad data using the machine learning. After collecting only bad data, maybe it is good to apply any scripts. So this is rough idea, but it is under brainstorming. So maybe I need to try and error. So, but yeah, any applications could be okay. yeah, that's all from me.
Yeah, I think something that I learned from trying to remove RFI from several different bands, because like I mentioned, I have a maser monitoring project, and we look at the main lines of OH at sort of 1600 megahertz, but we also look for other transitions in other parts of the band, and I found that there's quite a lot of difference. Obviously, it's because of the different sources of the RFI, but that sort of a method that works in one band doesn't really work for another band. The kind of RFI that's very, very localized in frequency, intermittent in time is great, but if you have something that's persistent in time, which I've got some examples. I don't know if it'd be worthwhile sharing some of these hideous plots that I have of RFI to show you what I'm talking about. Hold on, let me see if I can share just this one. So if you can have a look here, hideous. This is before. Oh, can you see? You can see a plot, yeah? Yeah, cool. Okay. I've got the little green outline, says we're ready to go. This bit at the top here is kind of all of the data. These are different polarizations. I don't remember which one I labeled as which. This is just diagnostic plots for me. But you can see how it's like very, very, there's this periodic, almost sinusoidal shape in frequency, which is super annoying because it's my signal, if there is a signal, would be kind of what's left behind in the bottom here. So this is just me trying to fit and remove this kind of sinusoidal shaped frequency modulation, which I have no idea what it specifically is. I imagine, yeah, it's the mobile phones. But yeah, I think, sorry, and another thing that I tried to do here, I wasn't able to find an example of it just easily. But there was another example where it was very, very, very fine. I don't think these plots will actually show it, but yeah, like every third channel. And with that, I did I tried to do a clustering algorithm with a machine learning clustering algorithm to try and identify which channels were bad and which channels were good, with the idea of trying to define regularly spaced things that I could then remove and flag those individual channels and hoping that something stays behind. But yeah, of course, I don't know if the baseline that I'm seeing is actually absence of signal or what's going on there. But yeah, I think having something tailored for the different sources of RFI is definitely the way to go. So does anybody else have any more comments or questions? All right. Silence says no. All right. Well, thank you so much again to our speakers, Nobuyuki and to Tommy. Thank you for sharing with us your work and struggles that we can all relate to. And yeah, we'll keep the conversation going on Slack. If you have any other questions or if you'd like to reach out to any of our speakers about anything, please do so through Slack. And thank you. We'll end the session a little bit early then. So thanks everyone. See you next time. Have you seen how sometimes I don't think Zoom does this, but Teams does it where it like recognizes things you say or gestures that you do, and it throws up, like if you do a thumbs up,